Okay, so it's playtime. So you guys want to learn a little bit about DC to DC converters. So I'm going to do a few experiments here, and I will just like probably pack up and set up each experiment before I record each segment. So first things first. This little guy here, I've just set it up. This one's pretty common off of Amazon, but there's like tons of them. I'm actually working on a presentation to show you guys later on in the video describing different sources and types. Here's another common little DC to DC hobbyist converter. I mean, you can probably put it in production. I wouldn't recommend it. I'd recommend using something that is pre-built, assembled. You know, it's got a decent heatsink and all that on it, but you don't want to run a tower or whatever off this. But this guy here, you can pretty much put in, I think it's 10 to 60 volts, and you can get anywhere from 2 to 80 volts out of this side. So this is basically like a portable variable current, variable voltage power supply. So that's one. Another DC to DC converter. Let's see here. Can I reach it? Yes, I can. All right. Of course, is this guy here. These guys you can get on Amazon. They work. They are pretty reliable. They're pretty robust. And then here is another common one. This is actually a step down that you typically see in off-grid systems. So if you've got a 24 volt system but you need to run 12 volt stuff, you don't want to tap off your battery bank because you'll screw things up. So you use one of these guys here, which you simply, here we go, you just, if I can get it out of the parcel, or the packet, whatever the hell you want to call it, there we go. So if you've got an off-grid site or a home or a cottage and you're running like 24 volts, any 12 volt stuff, you can just run it off this. This one I believe is good for 15 amps. Yep. Input 20 to 30 volts DC, 15 amps. So for all of you wondering what the official variance in the 24 volt DC system is, there it is officially, 20 to 30 volts, 15 amps. Okay, and it says right here that the output, of course, is 15 amps peak, 24 volts. There's the specs on the little bugger. Alright, so what I've set up here is our first experiment. And this is to show you, and by the way, my bench power supply is pretty clean, so I've tested it with my other scope to make sure, and it's about the same kind of cleanliness as a battery. So now the reason why I've got the oscilloscope here and that is to actually show you how clean well, compare the power in and out of here. I wish I had a way to capture that, like a separate camera or something. I'll figure that out later anyway. But let's see here. I believe, there we go, blue is the input, so blue is the top line. That is the 12 volt input, and then yellow is the 24 volt output, because this is a 3 amp, 12 volt in, 24 volt out boost converter. Okay, and this one here, of course, you can get I think it's 72 watts out of it. This is pretty common. Like if you're running a 12 volt off-grid system, you know, just to save money and whatnot. Let me just reset these guys. Just to save money and whatnot, then of course what you can do is run the whole solar system off of a 12 volt system. Where is my current? Yeah, there we go. Run it off 12 volt system and then use this to get your 24 volts to run your PoEs and your equipment. But if you're not running stuff that's critically in need of 24 volts, you can usually run it on 12 volts. So anyway, let's take a look at some interesting things on this. This is why I built this little guy. Okay, so watch this. I've got 13.2 volts going in right now. Now, this meter here is the output. This is the current being drawn from the 24 volt side. And this guy here is the input, if you can see that. But I'll read it off to you just in case, because I need to get a third multimeter. Maybe two more for these kind of experiments. Maybe just something that just has a big screen on it, but it has like current and voltage. That'd be really nice. So I'm sitting at 13.2 volts right here. Now watch. And especially keep an eye on the scope. So if I drop, I'm down at 12 volts now. You'll see the output is still 23.9 volts off the output side, right? This is one of the key features of DC to DC converter. As I roll down, 11 volts, still 23.9 out on the DC to DC converter. That's what it's doing, is it's actually compensating. It'll consume more power, or the same power, but increase the current on the input side as the input voltage drops to compensate and keep the power consistent on the output side. So now let's go down to the danger zone. Danger zone! Okay, 10.9 volts. Still 23.9. This is where things get shaky, especially under load. 10.4, 10.3, 10.2. I believe there is just some cutoff voltage. And here we go, 9.9, still 23. As you can see, I'm really cutting the voltage down here. There we go. So at 9 volts, it destabilizes and the circuit collapses. But as soon as you come back up to about 10.5, it will work. Okay, even at 14, if I go up to 14 volts here, you can see that's still good. So now let's put a load on here. Wouldn't that be cool? Okay, so let's turn on, let's get about the maximum that this DC to DC is capable of, okay? So here, I'm going to go, let's see here, 3.6 amps. That's a little bit hot for what this thing's designed for. It says that its rated capacity is 3 amps. So, yeah, we've got our power there. You know, I should have considered is that that's bloody bright. So maybe I will move it slightly out of frame. And there you go. Over there. Okay, so as you can see here, we've got 3.5 amps being drawn on the 24 volt side. And down here, it's showing 7.7 amps being drawn from the 12 volt side. You see what happens there? And a lot of people screw this up and they don't take that into consideration, is that the amount of current you draw on the 24 volt side is going to be doubled at the lower voltage because your power is your constant, okay? So at 12 volts, you're going to be drawing roughly twice the amount of current, plus whatever the inefficiencies are of the DC to DC converter, of course. So looking over here, and of course my leads have a bit of voltage drop. I've got 12.4 volts at 7.7 amps. Okay, so again, 3.5 amps at 23.3 volts on the 24 volt side. Let us now screw with the input power. All right, I'm at 13.1. Let's dip her down. You'll see the voltage drop on this line here. Okay, on the blue line. So I'm at 12.8. As you can see, the current and voltage are still consistent on the output side of this, but you'll see that the current has increased now. At 12 volts, I'm getting 8.1 amps on the input. Okay, let's dip a little bit lower. This get really dangerous. Okay, I'm at 11.7, and now you'll see that it's 8.3 amps on the input. So you see, as the voltage drops, the current increases to compensate and create the power at a constant, right? But again, nothing's moving here. 3.5 still, 23.3. Let's dip her down a little bit more. And what's going to be really cool is when we hit the point of instability on this DC to DC converter, and she pukes and does all sorts of funky stuff. That's the fun part. And you'll be able to hear it too. Hopefully I won't filter it out on here, but I'll put it on. Okay, so I've got it down to 11.2 volts, and we've got 8.7 amps drawing on the 12 volt side, the input side of the DC. Okay, still dipping. This is where things start to get rough. And if you watch the waveforms here, you'll see that things start to get a little dirty as this little guy starts to cough and sputter. So we're at 10.7 volts, 9.2 amps on the 12 volt side. Okay, let's get really scary. Look at how dirty that's getting, okay? On the input and the output, because this little DC to DC converter is panicking. It's like, what's happening here? We're almost at the cutoff voltage. Okay, and you can actually see this losing stability because the 23 volt side is actually dipping a little bit. Let's see here. Yes, okay, so we're going to dip right down here to the point of stability loss. Okay, so we're at 9.6 amps coming in the input side at 10.3 volts. Oh, we're getting close to failure. Just slowly rolling the voltage down. Alright, what? 9.9 volts on the input side. At this point, your batteries are really hurting. You don't want to do that. 9.7 amps. Okay, and you can see that the output side is starting to suffer a little bit too. Now we're losing our consistency. It's down to 22.5. Here we go. It should topple at any point. Oh. There we go. Come on. Want to get to that sweet spot where the thing really freaks out. Might not be able to do it at 3 amps. Okay, we are at 9.6 volts, 9.7 amps. Come on. There we go. Now see that? Notice the lights went half bright. We're at 17.6 here because the actual circuit collapsed. I'm not sure if this is capacitive or inductive. I'm pretty sure that's an inductive boost circuit, okay? It's using a couple of coils in there, basically, like almost like transformers to pulse and create a higher output voltage than, you know, the input voltage. So look at that. She is freaking the hell out. We've dropped down to 17.7. It is not happy. Our current's still kind of consistent, so this is making sure that the current stays about where it needs to be, even though it's sacrificing voltage here. Alright, so you can also hear this. Listen. That's the giveaway that there's coils in there. So, got little inductors. Okay, a little bit more. Listen to this. Circuit's pretty much ready to collapse. She is noisy as hell on both fronts, okay? And at this point as well, you're going to see that your equipment's starting to get a little weird, possibly, because there's so much noise on the DC bus. Let's see if we can topple it. We're sitting at what is that? 9.8 volts, 6.2 amps. Okay. Ooh. Alright, it should be at the cutoff voltage almost. There we go. She just died. There you go. So that's 9.7 volts, and as you can see, this guy is coughed out. 2.1 amps, 8.7 volts. So this is not working anymore. Your little DC to DC converter has said, I can't do it. Now let's power it back up and see what voltage is the let's see here, the restore voltage. 9.7, 9.8, 9.9, should be around 10 volts. There we go. Approximately 10.5. I don't trust this meter, but my bench power supply is 10.5. So we have recovery, full recovery, well, not full, but we have recovery at 10.6. And let's see here, as we climb up to 11, 11.2, 11.3, there we go, 23 volts, 11.4, 11.5, 11.6, 11.7, you can see it's pretty constant, still at 23. And this meter might be out a little bit anyway. I'm also loading this thing to its full capacity. 12.5, 12.6, 12.7, 12.8, 12.9, 13. Let's just jump to 13.5, which is float if your system's running well. Still 23.2. And as you can see, the waveform is extremely clean. That's just office noise. It's fans and crap that's running in here. Okay, let's hit 14.2 volts. Okay, we're at 14.2 right now. We're still at 23.2 and 3.57. We'll drop this. Okay, as I decrease the load, as you can see, the voltage comes up a little bit more, and poof, 23.9. There we go. Isn't that cool? Alright, so that's the first one that I wanted to show you guys. And, alright, so there's our little experiment for the first little generic eBay, Amazon DC to DC converter. Now, I haven't put these into 100% duty cycle yet. I use them for lighter applications, and they tend to work fairly reliably, so, yeah, they're decent. Okay, so I'm going to jump cut over to the next one, and I'll bring out this little hobbyist jobby right here, and we'll take a look at it. And then I want to show you the step down. That'll be the interesting one. Not many of you guys are going to use the step down, but hey, I want to do a comparison of many different types. Alright, so here we go. I'm going to pause this. Okay, so let us take a look at this cool little hobbyist one. These guys are really handy if you need a specific voltage. You can get DIN rail mount ones, which I'll cover in my little boring part of the video where I do some, like, you know, presentation and shit. But this guy here, you can actually adjust the current. This is the constant current adjustment, and then there's a, I'm not sure exactly why that one's there, but whatever. It's not necessarily labeled either. What does it even say there? Whatever. This one over here, that's the output voltage, which you can see is currently at 21.4. My input voltage is 13.6, which you should be able to see there. Now let me just adjust this little screw here. I can turn it up to whatever friggin' voltage I want, up to 83 volts is where I've tested it. And there we go. I'll put it at 24.2-ish. Alright, let's see here. I'm going to load it. Oh, I think I see what that guy's doing. That's interesting. Oh, I'm getting a low... That's what that blue is. It means low voltage right there. So this thing's surging quite a bit. I haven't actually played with this one at all, really. Let's try adjusting that. There we go. I ordered this thing in just to play with anyway. Let's see here. Apparently it's good for 30 amps. Yeah. UVLO. So I'm not sure exactly what that one says, but maybe that might be what this is for. Okay, let's do this again. So it seems as you load this guy, she turns off. It's not cool. It's not supposed to be doing that. This might be the low voltage cutoff. That might be what... Yeah, that's the low voltage cutoff. There we go. Let's turn that way up. There we go. Let's try that. Oh. Interesting. It's a good thing we are playing with this thing before I actually put it out in the field. Like I said, though, I don't know if I trust it entirely. What do we got here for voltage? Oh, that's interesting. My input voltage has dropped dramatically, and I'm getting high current. That could be what it is. Let's see here. 3.5 amps. And then as soon as I put the other one on, it jumps right to 10.4 amps. That's really interesting. My current draw here is only 1.8, so let me just play with something here. What does this thing do? Because clearly it has something to do with the weird little issue we're having right here. There we go. Yeah. Well, anyway, I'll just leave this here because it's working. You guys get to see it. So, we have our... Just making smells. It smells like onions. Alright, so, another DC to DC converter. Alright, pretty cool. We're already playing with it. This is fun of science, right? People love this stuff. I want to make sure that's not burning. Yeah, this is an eBay purchase, by the way. Alright, she seems good. It's not getting too hot. Okay, cool. Alright, so I'm going to turn up the output voltage just a little bit more to get it up to 24-ish. So this isn't... probably wouldn't be a better one to choose from, because as you can see, the voltage is a little wonky on it. There's a few little quirks, and it could just be that I didn't read the manual on this bloody thing, but whatever. So, once again, 3.6 amps here on these 4 bulbs, 24.2. Now, let us dip the voltage a little bit, and this might actually cut out at an earlier voltage, because, no, we don't know what quality this thing is. I was actually going to use this thing to make a portable variable output power supply, but I'm dipping down here. I'm at 12.5. As you can see, still consistent, 24.2, which is what you want a DC to DC converter to do. Whether it's a step up, step down, or it's a constant voltage. Alright, as I'm decreasing the voltage, same characteristics as the other one. The input current is increasing. There we go. And as you can see, it's pretty steady waveform still. No noise or disruptions or instabilities just yet. So, yeah, it's not too hot. Okay, so we're at 11.7. We're almost at the limit of my bench power supply, which is 10 amps. And then my current limiter kicks in. 11.3. There we go, 10 amps. Okay. There, my bench power supply faulted. So I might have to take one set of lights off. There we go. Okay, so still the same output power, or voltage I should say. Power, voltage, and current are different things. 10.9, 10.8, 10.7. This one may hit a instability point. It may not. It may just have a cutoff voltage. There we go. We're at 10 volts, which is 9.5 on my little guy here. 5.4, 5.5, 5.6, 5.7, 5.9. There we go. So there's our point of instability. It's roughly around 9 volts. That's when we see the voltage topple. Our circuit starts to collapse there at an input voltage of 9 volts, which is to be expected, right? I mean, there's only so much these little guys can do. But this one here, if you'll notice, at 9 volts, as I go down by millivolts, the output voltage is dipping. Okay? There's that UVLO coming on. I believe that's the low voltage. Okay? Which actually, I wonder if let's try adjusting that just quickly. No, we're in the middle of an experiment, but whatever. Yeah, that's the low voltage cutoff, I believe. Or low input voltage. Wasn't that interesting? That is pretty cool. It's pretty damn cool. So here we go. If I can actually turn this little guy up a little bit, and even though I'm at a lower voltage, it's staying pretty consistent there. Let's dip the voltage even more now. I have not played with this DC to DC converter, folks. Not really. Not to the extent that we are right now. Okay, now here we go. We're at 8.5 volts. Our little low voltage indicator's coming on here, and you can see that it's starting to get dirty. She's not very happy. We're at 10.5 on the output. Yeah, this is where she starts to dance. 8.7. And there we go. It looks like the output is just bridging now. It looks like. Yeah, you can see. There we go. I'm down to like 6 volts. If your battery's at 6 volts, by the way, chances are you should probably replace them. There we go. It's not nearly as dirty as the other one, but the other power supply definitely appeared to be better. Now let's see what the recovery voltage is. And at this stage, sorry, the recovery voltage is 8.7 volts. At 8.7 volts, it came back up at 22.4. Oh, went kind of funny there. Didn't like that. Oh, yeah, there's a little bit of a dip there. Somewhere around that's a strange characteristic. Maybe I should do a bit of a exploratory video on this little power supply. And look at that, isn't that weird? So the waveform on here, okay, blue is my primary, my input. My input voltage is just wonky as hell on here. I wonder if that's the power supply doing that? It must be this. It must be, because my bench power supply is pretty clean. That is so cool. So this thing's struggling right now to keep this up at a decent running voltage. And as you can see, yeah, the input is just all over the place. Look at that. Oh, this is cool, eh? 9.2. Oh, let's see where it really stabilizes. 22 out, 23 out. We're at 8.7. It's because we're under 9 volts. That's what it is. It's freaking the hell out. Let's see here. We're going up. Cleaning up a little bit. Let's see what happens when we hit 9 volts spot on. 9 volts, you can still see it's a little chaotic there on the input. The input's just going nuts. That is so cool. This is a really neat experiment, eh? But we're back up to 24.4 on the output, so we've actually we've recovered. Okay, so let's see where the input voltage cleans up, because you don't want any noise anywhere on your DC bus when you're running radio equipment. 9.5, 9.7, 9.8, 9.9, 10, 10.3. Let's see here. Let's clean up a little bit. 10.9, 11, 11.2, 11.5. There we go. 11.9, 12. It is not. So that little, we need to find out what that little adjustment knob does. Because clearly, there we go, 13 point, that's float. Clearly, this guy here Oh, it just cleaned up. Or is it that touchy? There's no way. That is interesting. Yeah, let's play with this knob again. I should be using a plastic one if it's that touchy. There we go. Note to self, if you're playing with one of these guys, you may want to put it on a scope while you're doing so. There. Oh, nope. Still noisy as hell on the input. Yeah, I'm not sure. I gotta figure out what this friggin' knob does. Oh, it's cleaning it up that way. We'll go another half turn. This is a noisy little DC to DC converter, folks. I don't know if I like that. But, yeah, just noisy. That seemed to happen once we started really playing with this thing. So, note to self. This is a dirty DC to DC. Okay, so, remember, well, this one's variable, so you can put whatever in and get whatever out. So you can actually use this as a 1-to-1 or a 1-to-2 or a step down. You can do whatever you want with this guy here, which is kind of the handy part of it. And as you can see, the output voltage is relatively clean, even when we increase the load on it. Let's see if I can hit one more bank of lights, because this guy here claims it'll do 30 amps. And that is a bold-faced lie, we have just found out, because clearly 3 banks of lights, you know, it just dipped. Let's see if maybe adjusting this will fix that. Let's see. Yes, it's got a current limiter on it. Ooh, isn't that cool? Look at that. Oh, you know why that's doing that? It's because my my power supply, if I increase the voltage, it'll actually decrease the amount of current being drawn. There we go. Okay, so now, I wouldn't normally do this, but this is an experiment, right? Okay, so this guy will take anything in and spit anything out, pretty much. What I've done here to compensate for the lack of current on this bad boy is I've increased my bench power supply voltage to, let's see here, 18 volts. I can go up to 45 before my little scope here panics. So we'll go 20. And then we can still see the waveform. Alright, so I'm at 7.4 there. We're at 5.4 here. Let's see one more. Yeah. Okay, so we still need to adjust the current on this. Let's see, a little bit more. Here we go. Why'd you go into standby? Stupid battery saver. Alright. I think if I do this, this will crank it way up and I'll be able to get the full current capability out of it. It's a neat little, this is kind of a neat little unit though, eh? There we go. So now, we are pushing 7.23 amps at 23.8 volts, which is kind of what we were shooting for. Up here I've got, so that's about 200 watts I'm drawing off of my bench power supply, because my bench power supply is at 20.0, and I'm seeing 10.2 amps drawn. So let's just increase it just a tiny bit more. I want to see the lower meter hit 20. There we go. So we got 9.8 amps here, 20.2 volts. And oh, the waveform up there is doing something really funny. Let's go over there and see that. We'll turn up the voltage a little bit on this bad boy. Oh shit. What are you doing? What are you doing to me? There we go. So I've got it at 10 volts now. And there we go. Maybe let's try this. Let's do another little thing. There we go. Alright, so I've put my 10 times on my probe, which means that I should be able to do this. There we go. Ah, there we go. Alright, so now as you can see, this is actually kind of noisy. This is a noisy little DC to DC converter. Isn't that interesting? So, Yeah, there we go. So, yeah, there's a little brief rundown of DC to DC converters. That's the science project experiment part. One last piece I'm going to do is I'll do another quick clip just on the step down. I don't actually have a one-to-one handy, but this is almost operating in one-to-one right now. In fact, actually, you know what I'll do? Let's put it in one-to-one. Okay, so I'm going to put 24 volts into it. Alright, so there's 24.8 going in. So this is pretty much doing a one-to-one conversion right now. Straight across the board. We got 24 down here. We got 23.8 here. If I turn up the voltage just a tiny bit. Yeah, almost there. There we go, 24. Alright, so yeah, that is operating as a one-to-one DC to DC converter. And the benefits of running a one-to-one, by the way, is if you want to make sure that you always have 24 volts out, even when you drop the voltage. So when your battery bank is dipping down because your batteries are depleting, your DC to DC converter will always make sure that you have a 24 volt output, or 48, or 52, or whatever the hell you want to run. So like even here, again, look at that, just wild, the kind of noise that we're getting off of this bad boy. Actually, I'm going to turn off one of these guys. Alright, there we go. So we're at 7.4, so I'm at 20, still 24 out. 18, we know that we can go pretty low with the input power before we start to lose this, so yeah, there you go. And it is your DC to DC converter, or boost converter, and one-to-one conversion. Alright, so now I'm going to jump cut one more time, and I'm going to show you a step down in operation, and then we'll move on to the boring part, the graphs and picture-y type stuff that I've kind of cobbled together just so you guys have like some variety to look at. Alright, hold on, here we go. Okay, this is the last part of my little science fair project here. Alright, so we're going to set the, this is the down converter. So this is a buck converter, not a boost converter. It says it'll operate from 20 volts to 30 volts. So first of all, let's put that to the test. Let's go under 20. What does it say right here? And yeah, we'll go to 19. Let's see, we'll go to 18. Oh, we're starting to waver at 16. That's interesting to know. Okay, so I'm going to put it back up to like full battery. So we'll go 24.8 roughly. Okay, input. Alright, so that's that. Alright, so this is 24 volts in, 12 volts out. So let's load it now, because it says it'll do 15 amps. So there's our waveforms. Yellow is out, blue is in, of course, and it looks like the input side of this thing is a little bit noisy. Okay, turning on. Oh, it seems to clean up the more you load it. Alright, let's actually take a look at this closely. Okay, so this is 12.9 output right now. Alright. And as I add 1.8 amps here, I'm getting 12.6 amps there, and I'm getting 1 amp on my input side, okay? So this is kind of backwards now. So since we're getting 12 volts out, which is half the voltage we're putting in, whatever the current is on the output, it's going to be roughly half on the input, depending on the efficiency of the device. So let's add another set of bulbs. Okay, we're at 3.6 amps out. 2.1 in, still 24.8 on the DC power supply, 12.4 now, which is pretty much it's a pretty much an 80% full battery. And as you can see here, the waveform's almost perfectly clean now. Alright, there we go. 5.3 amps, 12.2 volts. So it's dipping a little bit as we load it up. Okay, I'm being interested to see if what it would consume at about say 15 amps. I might actually be able to do that. I think I've got a light bulb that'll run that. Okay, let's go full bank 7.10. Alright, so we've got 7 amps on here right now. And yeah, at 7 amps, we're drawing 4 amps off the input, off the battery, I guess you could say. We've got 12 volts on the dot right here. That may actually be the where it'll sit, even if you load it down some more, but yeah, I'll experiment with that, and if I do see anything really interesting happen, then I'll let you know. I'll play with that afterwards, because the video is already getting pretty long. Now let's see what happens as we decrease the input power. Alright, so here we go. We are dropping. Oh no. Actually, let's go up first. We didn't do that one yet. 25.4. I'm still getting. This thing will do it 30 volts, by the way, which is equalizing voltage. So as I hit 29, as you can see, the output voltage increased by like a millivolt. Let's dip down now. So we are at 24.8, so that's pretty nominal. 23.1. Alright, so that would be 11.5 right there on each cell, but we're sitting at 23 in and 12 volts out, still 7 amps constant, but our input current is definitely increasing. 21.5 volts on the input, 4.8 amps. You can still see pretty rock solid there at 12.0 volts at 7 amps on the output. Now we're getting to the cutoff voltage. I believe this is where this little bad boy is going to shut itself down, which any good device will, especially on a green system or a remote power system, because you want it to cut off before your batteries get damaged. Also before you overcurrent anything. Alright, dun, 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 dun. We're down to 0.7. Oh, 19.9. So this is actually, it's actually running lower than its rated input voltage. 20. So your batteries are dead right now. 19.5. Yeah, the batteries are pretty dead now. Okay, let's see what we got here. 19.7, which, let's see here. Keep it going. Of course, the current is increasing. So I've got 5.3 amps in, 7 amps out as the voltage decreases. I'll bet you this little guy could probably go to about 12 volts and keep running. You can usually hit the equalizer, the balanced voltage on these guys. I'm at 17, 16. Oh, there we go. We lost it. Here we go. So where did we lose it again? So there we go. So at about 18.9. Actually, this is pretty consistent now between the two. Likes the higher voltages, I guess. 18.5. It seems 18-ish. 18.7. Now, instead of actually cutting off, it's actually not cutting off. It's just destabilizing. You can see that in the waveform there, right? It's pretty clean right here at 12. And then as soon as she dips, you can see her nice little ripple there. So, yeah, let's see what voltage the actual low voltage disconnect is, because I don't see a low voltage disconnect functionality on this guy. Alright. Oh, that's bad. 16.2, 15, and the output voltage just keeps falling with it. Oh, 14, 13, 12. I'm going to just shut off a couple of these bulbs just in case. I don't know if, I don't want to put a lot of current through this guy as I'm doing this because I don't want to damage it. Here we go. Look at that. 11.5 in. We're getting 7.8 out. Yeah, it does not have a cutoff. This thing is just crashing. Okay, so at it looks like 6 volts, we start to lose the output here, and if I increase the current, I got nothing. So at 6 volts, that's when this guy will finally die, which means that if you have this hooked up to an off-grid system, it will run your batteries completely flat unless you use a low voltage disconnect on this. And because it says that it's a 15 amp device, let's see here, 13.8, and it's actually 15 amps on the input and the output, it says here, which means that it's 15 amps output total. Okay, so yeah, you're going to want to make sure that you get a decent low voltage disconnect on here. You're going to want like a 15 amp or a 20 amp on that just in case, but realistically 15 amps out would probably be about 8 amps in, so I mean a 10 amp low voltage disconnect would probably cut it. So yeah, there we go. And let's see what our recovery voltage is. When are you going to jump back? And it's not jumping either. It's slowly coming up with it. Okay, let's try that under load. Okay, let's load it. Here we go. So I've got one bank of lights on. There we go. So we've got power again at 7 volts. That is really creepy. 5 volts, 6 volts. So we're at 10 volts in. We're at 12 volts in. Yeah, there it doesn't snap. It's not like it's got a strict on and off on this guy here, but at 16 volts it'll generate 12, 18, 20, 24, 24.8. There we go. So yeah, this is an interesting little buck converter. It's a down converter. It'll take your input voltage and have it. So that's kind of cool. But yeah, it's interesting to see the characteristics of this. I haven't worked with a lot of these guys here because I usually design my systems to run on the a constant voltage rate across the system. So if I need 24 volts, I will run it at 24 volts and not use any 12 volt equipment typically. But yeah, this looks like a really decent quality one, so I'm not sure if the other ones are like this. So there we go. There is your down converter right there. All right, so now we're going to move on to the presentation portion of the video. Okay. All right, on to the scientific-y presentation part of the video where I try to look smart and show you guys some details about this product. Okay, so these are the products that you guys all want to use. DC to DC converters are critical in a lot of situations, especially where you've got things that don't like voltage variances and you're running off-grid systems or systems that have a lot of dynamic voltage range due to just the characteristics of the system or general operating practices. So perfect situations for DC to DC converters. Number one, an off-grid site running a bunch of radio equipment, which is what you guys are looking at. Number two, you're working with other equipment that's operating at one voltage, and you need other equipment to operate at a different voltage. Let's see here. Number three, your cell phone chargers. If you look at these little thin, slim, little tiny finger-sized cell phone boost packs that you use when you're desperate and your iPhone just died, those have a 3.2 volt to 5 volt boost converter built into them. They're only good for like about 500 milliamps, regardless of what any of them say, unless you actually get like a little power bank that truly does have 5 volt 2 amp output. But those are usually the more expensive ones, not the ones you get at the dollar store or Walmart. All right, now. What's another good DC to DC converter example that you guys use on a daily basis? Um, hmm, hmm. Yeah, I came up with a brain fart. All right, so anyway, let's take a look at some common ones here. So, first of all, you've got a solar off-grid site, okay? The voltage variance on that healthy site should be anywhere from about 23 volts up to about potentially 30.1 volt or 30.2 volts, maybe ish. Okay, so some equipment just doesn't like to go to the high voltage, but I did some tests and found that most of it doesn't have a problem. And so what I found was that yeah, if you want to avoid these issues, you can get something like a one-to-one DC to DC power converter, which takes 24 volts in and spits 24 volts out, which is the nominal voltage we typically use for passive PoE equipment or most PoE injectors. Now, if you're running 802.3 AF or high voltage passive PoE, it'll be 48 volts bus. Many switches like Natonics or whatever, Natonics is a really common one, have their own DC to DC converters built into them. So you can take, say, one of those DC Natonic switches, feed it 48 volts, and you're going to get 24 volts out of some ports and 48 volts out of other ports. But since you're doing that, you want to make sure that that's clean power going in there. Although I'm pretty sure that with that particular type of switch, it does its own DC to DC conversion, so it doesn't matter. As long as you're within a tolerable voltage range, it should give you specific constants out each of the ports. But let's just pretend that they don't. Then you need something like this. These guys here are all just pictures that I pulled randomly off the internet because, hey, that's where we get this stuff typically. Right here is a really good one. Meanwhile, by the way, Meanwhile and Samlex and AB all make incredible equipment for this application, like really good quality crap. So Meanwhile here, this is an example. It's a 12 volt to 48 volt dual 138 watt boost converter. So you feed your 24 volts in and you get your 48 volts out, and then you would use it to power your switch or your passive PoE injectors that are specifically meant for 48 volts or whatnot. And as long as the voltage is within a tolerable range of the DC to DC converter, then it will output that voltage. Most of the higher end ones will just cut out when they get too low. Many of the other ones pretty much need to have a low voltage disconnect connected to them. Here's another little one down here. This Youku, never heard of them, but I found this on Amazon. So this is in 12 volts, out 48 volts. There's another little one you can use inside of your enclosure. So if you're running a 24 volt off-grid system for a repeater site, you can use one of these guys. These little guys up here, this silver automotive-y type looking thing, I think was specifically designed for automotive. And the one I've got in my truck is actually 12 volts to 24 volts. I use it to power a Powerbox Pro and my 2 bullets, and that works pretty good. As you saw earlier in the video, you can see what its voltage ranges are and how it operates. Now, if you really want to get fancy and do a really pretty enclosure, you can go DIN-mounted stuff. And there's all sorts of DIN-mounted stuff. I believe Tycon sells a bunch of stuff on their site. AB. I'm not sure about Samlex yet, but I will be going to those web pages in a minute to show you guys those guys. Now, I've got some smaller cheapies here. Looks like they're Youku again. So these are some more streamlined ones. Of course, you just mount them. And then you've got your project boards like this, which work for the most part. You would want to run them at like 100% duty for like a solid 3 days minimum before you can trust them to put into production. So if you ever want to play with something like this that specifically meets your need, because usually with these guys you can adjust the output voltage to whatever you want to run it hard for a few days and see if it struggles or chokes or does anything funky before you actually put it out in the field. And with any of these DC to DC converters, whatever the current rating is or power output, you want to run them no harder than 80%. We're not talking power inverters here. These guys are quite a bit more efficient than power inverters. So with these guys here, the tolerances are a little bit more tolerable. Best practices on one of these guys. If you think you're going to need about 10 amps at a site, then use a 20 amp. Then you've got like plenty of room to grow. If you're just running a small relay site with like a couple of power beams, power beam ACs, and a router, you probably only need a little 3 amp jobby to do it, because I think you'll only be running like maybe an amp and a half for like that much gear right there. Which should be another video I should do, is radios and exactly how much power they consume. My cat is attacking my foot. Jeez, stop. What are you doing? Okay, so there we go. There's that brief part of the video. Now, let's go to the interwebs. I think I'm right here. Alright, so starting off, here's Meanwell's website. Meanwell make awesome power products. You can pretty much trust anything Meanwell, but be careful, because you can't always trust things that look like Meanwell. In China, in Shenzhen, they typically try to clone equipment so that you get confused when you're looking for something online. Like if you go to Alibaba or AliExpress or whatnot, you'll see something and be like, hey, that's Meanwell. You're not going to see the Meanwell logo on it, but it'll be the same type of enclosure as a Meanwell, and then you'll be like, oh crap, if I can buy that on Ali for like $5, that's a good deal. No, it's not. I've actually experimented with this, and I picked up a couple of 120 volt AC to 12 volt DC power supplies, PSUs, and they were rated for 5 amps, and when they ran them at 3 amps, they overheated and died. So I actually checked the specs on the FETs and whatnot inside of them and found out that the unit was only capable of maybe an amp at the most. So I was just like, I was very disappointed. So anyway, let's dig a little bit deeper here. So let's see here. We've got, this is the beautiful stuff. Look at this. Look, goodies. Yeah. Okay, so this is all the good stuff you've got to choose from. DIN rail, I prefer DIN rail. If you can mount a DIN rail in your enclosure and mount everything on that, that's beautiful. That's pretty. That's what you want. Let's take a look at the enclosed ones first, because these are the ones most of you will be familiar with. Okay. See here, nothing incriminating. All right. So, what do we got here? 15 watts to 150 watts. Miniature size, non-PFC. Let's see here, 300 volt AC input surge. So this is just a standard PSU AC to DC. It's the wrong one. We don't want that. We want DC to DC. Oh man, they make DC to AC inverters too in this style. That is very cool. Okay, but that's not what we're looking at right now. Let's see here. We want enclosed type DC to DC. There we go. Okay. There we go. Railway standard. That's pretty cool. So 30 watt to 300 volts. Or watts, sorry. Isolation 4000 volts DC. Half encapsulated. Here we go. So going through this list here, you can find specifically what you actually need. Here's your power inverters. Here's your DC to DC enclosed types. PCB type. This is if you're mass producing them, which I don't think any of you guys are going to be doing. There's some little tiny ones. I didn't realize that these guys actually made all of these different versions of it. But let's go back to the top for a second. There's your enclosure type. Let's see what they've got for DIN rail. That's what I really want to see. All right, so 4-to-1 wide input range, 2-to-1 input range. Let's see here. Fanless design, cooling by free air. That's cool. Yeah, less moving parts better, because if you've got a fan that dies and your equipment overheats, that's going to suck. Let's see here. Let's look up. This is probably either, yeah, that'll be the wattage is 1530. So let's take a look at the 60 watt. Let's see what this guy looks like. Pretty pictures, right? All right, so look at that guy. Nice, pretty DIN rail mount. Input. Let's see here. Let's scroll down a little bit. Here we go. Okay, so input. DC current. 9 through 36 volts DC. Output. Let's see here. 5, 12, 15 volts, 24 volts. Yeah, so you've got all of these different voltage ranges you can choose from. You just need to pick the product that you need specifically. But I do strongly recommend Meanwhile. They're just bulletproof, man. And look, ooh, wireless network, telecom or datacom system. Okay, let's get rid of Meanwhile now. We all love Meanwhile. Good stuff. Okay, so here's Samlex. SamlexAmerica.com. I love Samlex. In fact, I have a 2 kilowatt pure sine wave inverter sitting right next to me for my household backup battery bank, which we use when the power dies here, which happens from time to time in lonely little Kanukistan. So let's see what we've got here in DC to DC converters. We've got regulators, fully isolated regulated DC to DC converters, provide stable 12 volt to 12 volt or 20 volt to 24 volt. These are the one-to-one converters I was telling you about. So if you want to make sure that you've got a system, you've already wired your system for solar for 24 volts, for example. We're going to use that one because that is a very common one. Okay, then you get one of these bad boys here. Bam! And you feed it 24 volts. Let's see here. There we go. Let's check this out. I think this is the one. Okay, so 360 watt DC to DC converter. Let's see here. Here we go. This is what you want. Volts for an input DC voltage range of 20 to 35 volts and the rated output current of 15 amps. Let's see here. And where's the specifications? So there you go. 20 to 35 volts DC in. 24.5 volts DC out constant. So as I showed you earlier on in the video, with a power supply like this, and by the way, Samlex is rock solid too. Like, these are really good products. You can feed it anything inside of that range, which means full swing of an off-grid system and not have to worry about anything because you will always have a regulated 24.5 volts DC. Of course, there will be minor variances, as you've seen, as you load it, due to like wire resistances and whatnot, and just depending on the build of the device. So yeah, there's that. So there's one of the Samlex ones. That's a 1-to-1. So here we've got a step up, isolated step down. Okay, step up, step down. Yeah, that's pretty much all there is. Regulated, which is 1-to-1, step up and step down. Step up situation is great. Like, for example, if you've got an off-grid site and you don't need or you don't have enough equipment there to run at 24 volts, and say you're running it's just a single 150 watt solar panel is an example, okay, or maybe like even a 35 watt solar panel. Those guys typically output about 18 volts, 17, 18 volts nominal for a 12 volt system. You're going to be running that through your PWM or MPPT charge controller, and it's going to be feeding your 12 volt battery bank because you need to have a higher voltage off your panels than the battery bank you're running. So 18 volts is pretty much a 12 volt battery bank. So now you've got a small 12 volt system sitting out here in Farmer Joe's field on top of a hill, right? You don't have enough gear to build your bank up to 24 volts. So what do? You use one of these. You use a step up. There we go. Step up 12 to 24 volt boost converter. And here's a whole bunch right here. I chose the non-isolated just so I've got like some variety here. Let's see here. So let's look at, there's 24 volts DC to 12 volts DC. 24 volts DC to DC. Okay, yeah. Sorry, these ones are the step downs. Wrong. Okay, let's go back. There we go. Step up. Sorry. There we go. Okay, step up converter. Let's look at one that would probably be about the average size for what you need. I think these are based on amp. So let's take a look at the step 10 because I know it's going to be 10 watts. Yep, 10 amps DC. Okay, so once again, 9 through 18 volts DC. That's a full swing 12 volts off-grid system or battery. And remember, if your 12 volt battery hits 9 volts, it's probably in trouble. Output 24 volts DC, 10 amps. As you can see, it's nice and small. You just mount it to a board or stick it in your enclosure and you're good to go. Once again, Samlex, they kick ass. Also, if you're going to be running a site and you build your own UPSing or run a DC plant, but you're on an AC premise, then Samlex also make great AC to DC power supplies. Really beefy ones. Okay, so moving on. No, thank you. Okay, so Schneider Electric here. We're in the Schneider page. So these guys do the same thing. Schneider used to be Xantrex, which used to be Trace Engineering. Trace Engineering, once upon a time, was a great company for power inverters and DC to AC, AC to DC, whatever. They worked in primarily in off-grid systems and made all sorts of really wicked stuff. Then they became Xantrex. I can't remember if they got bought out by Xantrex or changed their name or what happened. Don't ask me. I don't know the history of it. I just know kind of roughly what happened. And then Xantrex went around for a little while. They started selling Xantrex inverters at Canadian Tire and whatnot. And then all of a sudden, boom, Schneider bought them up too. Because Schneider's been buying everybody up, which is kind of cool. They're going to be like the kingpins of electrical soon. Okay, so on this Schneider page here, you can pretty much find anything you want because these guys kind of specialize in this stuff. So direct current DC breakers, here we go. Converter module, 30 watt, 24.828 to DC 5 volts, DC 6 amps. So these are your, let's see here. Well, this is pretty much everything. I actually have a few of these solid state relays kicking around. Let me just, let's try looking for 12 volt to 24 volt boost converter. Okay, let's see what these guys have in here. Battery management, smart charging, remote battery management for that looks pretty cool. Alright, this probably actually is Ethernet enabled. I'll have to go back and take a look at that later. Okay, SCADA pack. Yeah, if any of you guys work with SCADA, battery management systems. Let's see here. Whatever, make a liar out of me. DC converter. Let's just, no, don't want versus. There we go. See if I can find this product that I'm trying to search for. I always suck at searching for things. This is why I call people. Let's see here. Yeah, they just have too much equipment. Alright, moving on. AB. I love AB. AB's been doing DC stuff for so friggin' long. So right here, smack in the face. Here's one of your, let's see here. What is this one? 24 volts DC in? Out 30.5 volts DC? Again, just an example. I was just looking for ones to show you guys. These guys make all sorts of different products. They also make DC breakers, which are killer. So yeah, this is a nice little DIN rail mount DC to DC converter. Nice little guy here. And so AB, that's another company to check out. And here's Tycon. Of course, many of you might already be familiar with Tycon, but if you aren't, you're going to see that these guys sell pretty much everything you need for the WISP. Okay, so looking here, this one is an 18 to 36 volts DC input. Let's see here, 24 volt DC, 2.9 amp, 70 watt output, which is, that's pretty much the same as the little funny automotive one that I showed you guys in my little demonstration earlier. So here's one right here that will ensure that you are running at 24 volts DC as well. And Tycon's a trustworthy company as well. They've got all sorts of cool stuff. Let's see here. Now let's go to where most of us buy our stuff, okay? This is for the other guys who are poor or just don't have a lot of money because you're a startup. Here's eBay. Of course, I picked ebay.ca because I am in Canada. So again, here's some here's some little chintzy ones you buy when you're making those little boost packs for your purse or whatever. Here we go. You can get a wide variety of crap to decent product on here. That variable in, variable out that I showed you guys earlier, that came from here on eBay. See, there's some sealed ones right there. That's not bad. Some smaller ones, but those are like low current, like 1 watt. Kind of useless for what we're doing, right? Let's see here. Yeah, there's another decent one. The ones that are in housings are typically what you want. So yeah, there's eBay, Amazon now. Looking at Amazon, there's all sorts of cool ones here. This one right here would be actually wicked for building a little bench power supply, a portable bench power supply. That'd be pretty cool. Actually, I think that's similar to the one that I've got right there. So this gives you some price ideas. If you're not in Canada, then these prices will be lower for you. Because as you know, anything coming into Canada is costing like a fortune because their dollar's worthless right now. So pretty much similar stuff that you would find on eBay, except in this situation, it's Amazon, so you can probably trust it just a little bit more than you can from eBay. Okay, let's see here. And here's just another search criteria. There we go. See, here's DROC, adjustable DC power voltage converter. AC 110 to 220 volts to DC 24 volts. Okay, so that's actually a PSU. DC buck converter. So this is yeah, down converting. Okay. 8 to 22 volts to whatever voltage you want. Adjustable power output. That's cool. So you can go 1 to 15 volts. Let's see. Are there any other decent ones in here? Here's another Yeco. Let's see here. Oh, that one's 5 volts. That's kind of useless for what we're doing. But the whole idea here is I'm just showing you guys some crap you can get on here. If you guys really want to look cool, but you don't care about reliability, you can get something like this. Because, again, test it first. And the one concern that I have with stuff like this is that if it's not conformally coated with urethane or acrylic enamel or epoxy, if the board sweats or humidity builds up on it, that thing's going to corrode and it's going to fail at some point. And it might fail in a epic manner. You never know with these guys. I mean, like, it could like burst into flames and take your whole enclosure out. Alright, so now that we've gone through some experiments and some products and blah blah blah, well, let's learn a little bit about them. I figured I'd save the boring part for the last part of the video. Alright, how does a DC to DC boost converter work? So this is stepping up voltage. Okay, go, shoot. Okay, it consists of a high-frequency oscillator powered by the DC input. A regulator allows pulses to flow into a capacitor, or capacitors. The load varies. The capacitor's output is filtered to produce the DC output. A DC to DC converter converts one DC voltage level to another DC voltage level. Yeah. Here's how you use Google. And there's tons of little things about how they work here. You want to see a schematic? We'll just skip over to it quickly. Like, this is how to make your own. Like, they're not that complicated, but if you build them right, they can be really reliable. And yeah, let's close this one. Okay, here we go. This is a little bit more in depth. I went to Quora. I find a lot of interesting stuff on here. Alright, consider the circuit below. If the switch is on, the output voltage is Vin, and if the switch is off, the output voltage is 0. The percentage of the time when the switch stays turned on is called the duty cycle. Now, if the switch continuously turns on and off, then the output voltage will look something like this. This is pretty much PWM. Um, so what they're doing is they're charging a capacitor based on the pulses, kind of almost like, tapping a flywheel every now and again with a stick. We can get different output voltage waveforms with different turn-on time of the switch. Now in the above image, average output voltage is shown by the broken line. Now you can control the average output voltage by just changing the duty cycle or the turn-on time. This is how any power electronic circuit operates. It just controls the output voltage by controlling the pulse width. This is also called pulse width modulation. Yes, and I'm sure many of you know that a while ago I was telling you about pulse width modulation creating noise on solar off-grid sites. As I showed you earlier in the video, with these DC to DC converters, it is switching at such a high rate that it is not generating a lot of noise. So this is perfectly fine for your radio equipment. And if you're using a good PWM charge controller, which will be in another video, less of an issue still. Now you can see that this is not a nice output waveform. We need nice and smooth voltage. So how do we achieve only the average value, eliminating all this high frequency noise? You already know the answer. Use an LC filter. Will smoothen the current, and C will smoothen the voltage. Okay, nice answer. Let's connect an LC filter. Okay. This guy is giving like full details on this. So basically you're just sticking a capacitor in here and an inductor. Clean it up, whatever. Yeah, there's a million ways to do it. Okay, but you're not making them. This is just to give you an idea of how they work, okay? Let's see here. So that was the boost converter. Let's see. How does a buck converter work? The buck converter is used in SMPS circuits where the DC output voltage needs to be lower than the DC input voltage. The DC input can be derived from rectified AC or from any DC supply. The switching transistor between the input and the output of the buck converter continually switches on and off at high frequency. Once again, PWM. Same way as a dimmer switch works. I just want to check something here. Let's see here. I might have actually had the wrong page on there. Yeah, actually, I think that the Quora thing I was reading to is actually for a buck converter. I'm kind of in autopilot mode right now. The difference is with a boost converter, you're using an inductor to increase the voltage and store it in capacitors, which are then sent off to your device, whatever it is, to keep the voltage up. Okay, so here is a buck converter. Let's see here. So again, PWM. So this one's actually showing you an AC PSU. So you've got your AC input being rectified. Yay. Capacitor on here to clean things up a little bit. Okay. And switching transistor, your FET, whatever. Flywheel circuit. Yeah, it's just cleaning things up. That's all it does. So you got your diode and your capacitor here, and then your load. Pretty good, pretty simple, eh? Let's see here. I'll read you a little bit more. The buck converter is used in SMPS circuits where the DC output voltage needs to be lower than the DC input voltage. The DC input voltage can be derived from rectified AC or from any DC supply. It's useful where electrical isolation is not needed between the switching circuit and the output, but where the input is from a rectified AC source. Isolation between the AC source and the rectifier could be provided by a mains isolating transformer. Yay. These are all basics. I mean, like, you can go on Google and find all this crap. Anyway, but I figured just to be complete, I would include some of it in the video. And of course, many of you will probably reach this part and be like, I'm done. I got what I needed. See you later. But if you made it this far, good for you. You're either really bored or fascinated. Okay? So, that is basically what I've got for you right now. Let's see here. Oh, and yeah, here. There you go. A little bit of stuff to look at. And here is a voltage multiplier circuit, which is commonly found in a fly swatter. There you go. So, any questions, leave them in the comments below. Any corrections, leave them in the comments below. If there's something specific you guys want to learn about, leave it in the comments below or shoot me a message, and I can try to put a video together for you guys, okay? But Yeah, that's the gist of it. And you can also go on YouTube if you want to look at more of the physics behind these things or electronic wizardry and watch a video on how people build and operate DC to DC power converters. All right, well, thanks a lot, guys, and have a great night.